For a brief moment in the 20th century, it looked like humanity had solved the problem of slow travel on water forever. Vessels that lifted their entire hull into the air and skimmed across rivers and seas at more than 100 kilometers per hour were not science fiction. They were real. They were selling thousands of tickets a day, and they were being exported to countries on 3 continents. And yet, if you go to almost any harbor in the world today, you will not find one. Most of them are gone, rusting in scrapyards, sitting in museums, or simply melted down decades ago. The strange part is that the very thing that made these boats special is also the thing that ended up destroying them. In this video, we're going to look at how a technology built entirely around speed eventually became a victim of that same speed, and why an idea that seemed unstoppable in the 1960s almost disappeared by the end of the century. The story really begins with one man. Rostislav Alekseev was a Soviet shipbuilder who, in the years right after World War II, became fixated on a single question: what if a boat never actually touched the water at all? By 1957, his design bureau had produced a working passenger vessel called the Raketa, meaning rocket in Russian, and the name wasn't just marketing. On its very first commercial run, the Raketa cut a journey along the Volga River that normally took over a full day down to roughly 7 hours. A train covering the same route needed 13 hours. People who had never imagined river travel could compete with a train were suddenly lining up at docks before sunrise just to get a ticket. The Soviet Union leaned hard into the idea. New models followed one after another: the Meteor, the Kometa, the Voskhod, all built from aircraft-grade aluminum to keep them light enough to lift out of the water, and powered by diesel engines strong enough to push a 50-ton hull to speeds of around 65 kilometers per hour. To put that weight in perspective, a 50-ton hull is roughly equal to the combined mass of 35 ordinary family cars, yet on its foils it could still slice across open water faster than most vehicles could legally drive on a highway. Later came the Burevestnik, an enormous vessel fitted with actual aircraft turbine engines that could reach 100 kilometers per hour on open water. These boats didn't stay confined to Russian rivers for long. Britain, Italy, West Germany, Greece, and Vietnam all bought licenses or built their own versions, running them on lakes, coastal routes, and busy river systems from the Rhine to the Mekong. For a couple of decades, it seemed like the entire world was about to switch from slow ships to flying ones, and shipyards that had spent generations building traditional hulls suddenly found themselves retooling to produce these strange aluminum flying machines instead. To understand why engineers went to such extreme lengths, you have to understand what water does to a normal ship. Water is roughly 800 times denser than air, and every conventional hull has to shove that mass out of its way just to move forward. The faster you try to go, the harder the water pushes back. Engineers can bolt on bigger and bigger engines, but past a certain point, almost all of that extra power just gets absorbed by drag instead of turning into speed. Alekseev's team took a different approach entirely. Instead of fighting the water, why not get the hull out of it completely? They attached thin steel struts underneath the boat, and at the bottom of each strut, they mounted a curved metal plate, shaped almost exactly like an airplane wing. At rest, the boat sat low in the water like any other vessel, but once the engine pushed it past roughly 30 kilometers per hour, water rushing over those curved plates generated enough lift to physically shove the entire hull upward, out of the river and into open air. It's the same basic principle that lets a small hand, tilted out of a moving car window, get yanked upward by rushing air. Except because water is so much denser than air, even a foil the size of a dinner table could generate enough force to lift a hull as heavy as a loaded delivery truck. Once the boat was airborne on its foils, the amount of hull actually touching the water shrank dramatically, drag collapsed, and speed shot up. It looked like engineers had cracked one of the oldest problems in naval design. For centuries, shipbuilders had accepted one rule as unbreakable. More speed required a heavier, more powerful engine, and even then, the gains were small and expensive. Here was a design that flipped that rule on its head, using geometry instead of brute horsepower. Engineers who watched early prototypes lift clear of the Volga described the sensation as closer to flying a small aircraft than steering a boat. And in a real sense, that's exactly what was happening. Confident after years of success, engineers in the 1960s decided to push their designs further, aiming for a new benchmark, 150 kilometers per hour, faster than most cars ever traveled on a highway. Larger prototype hulls were built and sent out for high-speed trials. And that's when things started going seriously wrong. At top speed, the new hulls would begin shaking violently. The vibration was severe enough to shear bolts, crack internal fittings, and throw crew members off balance. Captains were forced to abort test runs and limp back to port. When engineers pulled the foils out of the water for inspection, what they found was disturbing. Solid steel plates, thick enough to stop a rifle round, were riddled with tiny pits and craters, as if someone had spent weeks attacking them with acid or a chisel. Within a few months of running at these speeds, some plates developed holes straight through the metal. For a while, nobody understood why ordinary river water was tearing apart solid steel. The answer turned out to have nothing to do with the water pushing on the metal. It had to do with pressure. As water rushes over the curved top surface of a foil, moving at very high speed, the pressure in that thin layer of fluid drops sharply. Most people assume water only boils when you heat it, but that's not strictly true. Water will also boil, forming vapor, if you drop the pressure around it far enough, even while it stays ice cold. That's exactly what was happening on the upper surface of these foils. A storm of microscopic vapor bubbles was forming in a region of near vacuum pressure, even though the river itself was freezing cold. Those bubbles didn't stay stable for long. As the flow carried them toward the trailing edge of the foil, they entered a zone where pressure spiked back up almost instantly. Unable to exist in that high-pressure environment, the bubbles imploded, not gently, but violently, releasing a tiny, focused shockwave each time. This process is called cavitation, and on a foil moving through water at speed, it happens millions of times per second, in the exact same spots on the metal surface. Each individual implosion is small, but the cumulative effect of millions of microscopic detonations striking the same points, second after second, is enough to physically knock atoms of steel loose from the surface. Over weeks of operation, this literally chewed the foils apart from the inside out. Worse, the churning foam produced by all these bubbles disrupted the smooth flow of water over the foil, which meant lift could suddenly collapse, dropping the hull back into the water without warning. Engineers at the time struggled to grasp the scale of the forces involved, since nothing about it was visible to the naked eye. A single cavitation bubble collapsing releases a pressure spike that, concentrated on a spot smaller than a pinhead, can rival the force of a loaded truck pressing down on that same point. Multiply that by millions of collapses per second, hammering the same few square centimeters of steel hour after hour, and even the toughest alloys of the era had no chance of surviving long-term service at those speeds. Cavitation wasn't the only issue. Hydrofoils performed beautifully on calm, glassy rivers, but the moment operators tried running them on open coastal water, new problems appeared. Even moderate wind and chop would send the entire hull shuddering and bouncing, and passengers who had boarded, expecting a smooth, fast ride, were often left seasick and shaken. Rivers brought their own separate hazard, logs. A log the thickness of a telephone pole, mostly submerged and nearly invisible, could be sitting directly in a boat's path, and at 80 or 100 kilometers per hour, a captain often had no time to spot it and react. Hitting one at speed didn't feel like a bump. It hit with the force of a wall, because at those velocities, water simply doesn't have time to move out of the way. It behaves almost like a solid. The deeper issue was one of margin. A conventional ship sits low and heavy in the water, with a deck that might stand 3 stories above the surface. Waves rock it, but it isn't going anywhere. A hydrofoil, by contrast, cruises with its hull suspended just 1 to 2 meters above the surface, roughly the height of a standing adult, while carrying the weight and size of a city bus. That's an extraordinary thin safety margin for a vehicle moving that fast. Airplanes get away with small piloting mistakes because the sky is enormous and mostly empty. The surface of open water is neither. It's constantly rising and falling, and a hydrofoil captain has no realistic way to react in time to every swell. Engineers eventually identified 2 dominant failure modes. The first was simply the density problem again. At speeds near 100 kilometers per hour, striking a submerged log, or even a large fish, could deliver enough force to buckle an aluminum hull or shear a foil clean off. The second was what happens on genuinely large waves. If wave height exceeds roughly the height of a person, a foil can briefly pop clear out of the water and into open air, and air, being 800 times less dense than water, offers almost no lift at all. The hull, momentarily weightless, then slams back down onto the surface with a force comparable to dropping a car from a second-story window. This kind of repeated slamming cracked hull plating and let water leak into the structure, quietly wearing boats down long before their expected service life was up. Insurance and safety inspectors noticed the pattern quickly. Vessels meant to run for decades were showing structural fatigue after just a few years, and rising accident reports made hydrofoil routes an increasingly hard sell. Regulators in several countries began restricting operations to calm inland waterways only, cutting off open coastal service during anything but perfect weather, quietly closing off entire categories of profitable routes before fuel costs even entered the picture. Mechanical failures, seasickness, and safety concerns made life difficult for operators. But none of them alone killed the industry. What actually finished it off was money. In 1973, the global oil crisis roughly quadrupled fuel prices almost overnight, and hydrofoils were catastrophically thirsty machines. A conventional low-speed ferry sips fuel by comparison. A hydrofoil running on adapted aircraft turbines could burn, in a single hour of operation, roughly as much fuel as an ordinary car would use in an entire year of driving. While oil was cheap, operators could absorb that cost and still turn a profit. The moment fuel prices spiked, ticket prices had to spike right along with them, and passengers who had once happily paid for the novelty of speed switched en masse to buses that cost a fraction of the price. Route after route stopped being profitable. Companies laid off crews, mothballed vessels in remote docks, and eventually sold the hulls for scrap. What had been a booming export industry turned into a financial sinkhole almost overnight. Operators tried every trick to cut costs, reducing service frequency, running smaller crews, even slowing engines to save fuel, sacrificing the very speed that made the boats worth buying in the first place. None of it was enough. Once routes stopped making money, banks stopped financing new hulls, and shipyards that had built their business around hydrofoil orders lost their biggest customers almost overnight. Naturally, operators looked for a way to salvage their investment, and the obvious move in shipping is usually to scale up. In conventional cargo shipping, bigger is almost always cheaper per ton. Build a bulk carrier the length of 2 football fields, and you can move 1,000 tons of coal while burning barely more fuel than a much smaller ship, driving the cost per unit of cargo down close to nothing. Shipbuilders tried applying the exact same logic to hydrofoils, hoping to build enormous cargo-carrying versions that could cross oceans loaded with freight in a fraction of the usual time. It didn't work, and the reason is pure geometry. This is sometimes called the square-cube problem. If you scale every dimension of a hull up by a factor of 2, the surface area of the hull and its foils, which is what generates lift, only increases fourfold, following the square of the scale factor. But the volume of the hull, and therefore its total weight, increases eightfold, following the cube of the scale factor. Double a hydrofoil's size, and you get a vessel as heavy as a small train, sitting on foils that are nowhere near large enough to lift it. To generate enough lift for a genuinely large cargo hydrofoil, engineers would have needed foils so wide they'd stick out further than the length of the hull itself, making the vessel impossible to maneuver into any normal port, and they'd need a whole bank of aircraft turbines just to get it moving. The concept collapsed under its own math. Hydrofoils were permanently locked into being a passenger technology for light loads. Heavy freight was simply off the table, both physically and economically. That mathematical limit boxed the industry into a corner it could never escape. A cargo ship's business model depends on economies of scale. The bigger the hull, the cheaper it is to move each ton of goods. Hydrofoils were the opposite. The bigger you built them, the more disproportionately impractical they became. So while ordinary cargo shipping kept getting cheaper by building ever larger vessels, hydrofoils stayed stuck at a fixed, modest size forever. By the final decades of the 20th century, hydrofoils had essentially vanished from most passenger routes, and the real culprit wasn't a design flaw at all, it was the highway system. As governments paved thousands of kilometers of new roads and built bridges connecting towns that had once depended on river ferries, car ownership exploded. Intercity buses started running every hour. Rail networks got faster. Air travel became affordable to ordinary people. Against all of that competition, taking a hydrofoil started to look pointless. Why pay the price of a winter coat for a ferry ticket when a bus covering the same route cost a fraction of that? Passengers, unsurprisingly, chose the cheaper option. Terminals that once had lines out the door sat empty. Old boats were towed into dead-end inlets, where they sat rusting under open sky for years, until scrap crews finally cut them apart. It's worth addressing a couple of persistent myths here, because they show up constantly online. One claims that oil companies deliberately buried hydrofoil technology to protect demand for gasoline. Another suggests that modern engineers simply forgot how to build machines this sophisticated, as if some secret knowledge was lost. Neither holds up. There was no conspiracy and no lost art. What actually happened was a straightforward economic calculation. The shipping industry realized that the real money was in massive, slow-moving cargo vessels, ships the length of several football fields, crawling along at walking pace, but capable of hauling millions of containers full of electronics, clothing, and food across oceans at an almost negligible cost per item. Moving passengers quickly across water, by comparison, was expensive and risky, and land and air transport already did that job better. Water transport simply returned to what it has always been best at: cheap bulk cargo, not speed. It's a pattern that shows up again and again in transportation history. A flashy, exciting technology gets outcompeted not because it stops working, but because something more boring and efficient turns out to serve the same need for a fraction of the cost. Nobody buried the hydrofoil in a vault. The market simply moved on to something that made more financial sense, the same way it moved away from airships, steam-powered cars, and countless other technologies that were technically impressive but economically unsustainable. That doesn't mean the idea of flying above the water died completely. It came back in the 21st century, just at a completely different scale. Instead of building enormous passenger ships weighing as much as a freight train, engineers shrank the entire concept down to the size of a single human being. Carbon fiber composites, materials that weigh almost nothing but rival steel in strength, replaced heavy aluminum hulls. Small electric motors and lithium battery packs, similar to what powers a smartphone, replaced roaring diesel and turbine engines. And decades of accumulated computing power let designers finally model foil shapes precisely enough to avoid triggering the cavitation that once destroyed full-size steel plates. Today, that miniaturized version of the same physics shows up under electric surfboards known as e-foils, where a rider stands on a board, controls a small motor with a handheld remote, and glides silently just above the surface of the water. The same foils have also found their way onto small recreational sailboats and racing yachts, letting them slice through waves with a fraction of the drag. Nobody is trying to use these small foils to replace container ships or intercity buses anymore. They found a much smaller, much more sustainable home, in sport, in recreation, and in the simple pleasure of flying just above the water. The technology that once tried and failed to conquer mass transportation didn't disappear. It just found the one place where its strengths finally outweighed its flaws. A handful of ferry operators have even started experimenting again, this time with small electric-powered hydrofoil ferries designed for short, sheltered city routes, silent, efficient, and nowhere near the scale that doomed the original fleet. They're not trying to beat the highway or the airport this time. They're simply offering a quiet, smooth ride across a harbor, which turns out to be exactly the kind of job this technology was suited for all along. 60 years after Alekseev first lifted a boat out of the Volga, his basic idea is still flying, just at a scale, and for a purpose nobody in 1957 could have predicted.